Alright, good evening. Let's go on to our next topic here, which is, as you can hopefully see, inductive reasoning. And you might be thinking, well, what is that? Well, it's because we haven't used this word before. And this starts getting into what geometry is really about, wherein we did algebra. It was a lot of, here's a problem and solve it. So it was like, how do we solve a problem, right? Then we get to geometry, and it becomes more about why. So you have to really explain yourself using reasoning, right? And so the first type of reason we're going to look at is inductive reasoning. So this our introduction here, right? So our actual title of this section is Using Inductive Reasoning to Make Conjectures. And that sounds like super official, right? So let's get some definitions down. So inductive reasoning. What this is, oh, my alarm's going off, is reasoning to say something is true. So we say something is true because specific cases are true. And we're going to give some examples. Specific cases are true. So that's our first part. And then conjectures. This is like the math version of a hypothesis. This is what we believe to be true. Okay. So let's take an easy example here. Let's say we have a person and they're standing out at, I don't know, the movie theater. Okay. And they see a person come up and they have two arms, right? Two arms. And then they see another person and they have two arms. And they see a third person. And guess what? They have two arms. So they have specific cases of people who go to the IMAX have two arms. So the conjecture they might make, the statement they believe to be true, is they could say everyone who goes to the movies, what is our true statement here? Everyone who goes to movies has two arms. Okay? And that's using inductive reasoning. It's just a broad kind of, I see this, and I'm going to make a statement based off of what I've seen. Right? Not so bad. So let's look at another example, because this is mostly true. We can talk about why this isn't true. We'll come back to it here in a second. Let's take another example. Let's say, where's my new page button? There it is. Let's say little Johnny or Billy or whoever, and they go out to, this is a super awesome picture I'm going to draw right here. And cool. Oh, that was bad. Hold on, I can do this better. Okay. If you can't tell what I'm drawing, you're dumb. No, not really that dumb. They're going to the zoo. Clearly this is a zoo. Here's some like trees in the background, some bushes, and there's some water. It's a pond, or it's a river now. Okay, there's my zoo. Why is this going away? Okay. So, little Johnny he's at the zoo. He's got crazy purple hair. And what he sees at the zoo, so he goes in and he's at the zoo, and we're inside the zoo now, and the first thing he sees is a I don't know what kind of animal. He saw a kangaroo. Alright, so little Johnny saw a kangaroo. And then he keeps looking and he sees another kangaroo. And then he keeps going and he sees another kangaroo. And just because I have it. He sees another kangaroo. So based off of the evidence that Johnny has, what conjecture might Johnny make about the zoo? So Johnny thinks, just thought bubble. What is Johnny thinking? Hopefully you said this zoo only has kangaroos. And based off of his evidence so far, is his conjecture, is his hypothesis correct? Well, as of right now, yes. Yes, it is. Because all we have seen is kangaroos. So his thought that all there is kangaroos is true. So right now, true. But just using some common sense, is this actually true? If you go to the zoo, is there only going to be kangaroos? Well, no, hopefully not. There's probably going to be, let's say, a hippopotamus. So as soon as he sees a hippopotamus, what happens to his conjecture? It goes from being true to being false. Okay? So what we've introduced here is our third vocabulary word for the day. This is our, call this a counter example. Counter example. And this is all it takes to disprove a conjecture. So it's not that we're trying to prove his statement true, it's that we're trying to prove him wrong. We're trying to make Johnny look stupid. And we have succeeded using just one hippopotamus. Do we need to know that they also have, I don't know, an alligator? I mean, we could see that. That would also be a counterexample. So how many counterexamples do we need? We just need one, though. All we needed was this very first hippo to see that his conjecture was not true. Okay? So, conjecture's true until you provide one or more counterexamples. That's the basic idea here. So, inductive reasoning is making a broad generalization about something that's true based on what you've seen. Conjecture is a hypothesis, something that you believe is true based on that, which can then be disproved using counterexamples. Okay? So our example back here at the movie theater. What could be a counterexample here? Well, what if we're at the movies and there happens to be a guy who has 4 arms? Maybe he's got 6 arms because he's like Dr. Octopus. Okay? So we would call this 6-armed guy our counterexample. And then we would probably stay away from him because he has 6 arms. Don't mess with people with 6 arms. Trust me. Okay. So let's practice a little bit. So the first thing we look at is pretty basic, just finding patterns. So what is our pattern here? We have March, May, July. So what is our pattern here? Well, these are months. Duh. Do they go in order? Sort of, except between March and May there's April. And between May and July is June. So what we can say is it's not counting, or it's not stating every month, but rather it's stating every other month. So the next item, we'd skip August. So our next item would be September. Okay. How about our next one? 1/3, 2/4, 3/5. And we could get like super technical and find like the differences in this, but let's just look at it like small children and keep it simple here. Our numerators goes 1, 2, 3, so we can assume our next number is probably going to be 4. Our denominator goes up by 1, it goes 3, 4, 5, so we can assume the next one is going to be 6. Okay, and I guess we could simplify it to 2/3, but they didn't simplify 2/4, so let's just leave it just like that. Okay, and our fourth one, a little fancy here. We got line, circle, line. In this one we've got line, circle, line, but it's going sideways. So we went from 1 circle to 2, 2 lines to 3 lines. So this is 1 circle, 2 lines. This one is 2 circles, 3 lines. This one here is 3 circles and 4 lines, which means our next pattern here should be 4 circles and 5 lines. So based on the rotation here, this has gone up, down, left, right, up, down. So this should go left to right. 1, 2, 3, 4, 5 with 4 circles. Yay, we're finding patterns. Okay, that's not so bad, right? I hope that's not so bad. Here's some better ones. Complete each conjecture. So complete the hypothesis. So if somebody said the product of 2 even numbers is what? So what we can do is we can look at examples, not counterexamples. We want actual examples. So 2 even numbers. So if I pick an even number, I could say 2 times 4, and that equals 8. Some other even numbers, I could pick 6 times, I don't know, 10, which is 60. I could pick 10 times 2, which is 20. We could keep going. Hopefully at some point you see a pattern here. If I say 20 times 20 is 400, or I don't know, 8 times 6 is 48. What do all of our products have in common? They all happen to be even. Yay. Right? That one's pretty basic. This next one I like a lot better. The rule in terms of n for the sum of the first n odd positive integers is blank. It's kind of a mouthful here. Terms of n. Okay, the sum of the first n odd positive integers. Okay. So let's say n equals 3. So we want the sum of the first 3 odd positive integers. So the first odd positive integer is 1, right? Our next odd positive integer is 3, and then after that is 5. So the sum of those, 1 plus 3 plus 5 is 9. And this on its own doesn't really tell us a whole lot. So what we do is we go, let's look at our next one. So let's say n equals 4, right? So this is going to be the first 4 odd numbers added up. So 1 plus 3 plus 5 plus 7, well this is 9. 9 plus 7 is 16. So we have 9 and 16. It's not telling us a whole bunch. So if we go to the next one, and same thing, 1 plus 3 plus 5 plus 7. Our next odd number is going to be 9. So this gives us 16 plus 9, which is 25. Now hopefully you see this 9, 16, 25, and hopefully these numbers look like something. If not, we go backwards here. This is 1 plus 3, which is 4. Then we have 4, 9, 16, 25. Hopefully that definitely sounds like something. Yeah, if we put in 1 here, we get 1 equals 1. So we have 1, 4, 9, 16, 25. 1, 4, 9, 16, 25, and hopefully you're just sitting there screaming at the top of your lungs. These are all perfect squares. This is 1 squared. This is 2 squared. This is 3 squared. This is 4 squared. And this is 5 squared. So what does this tell us? Oh, hold on. Oh, I lost my mouse. Okay, okay. So we see, alright, I'll align these in a different color. Our first, our second, third, and it works out this really nice pattern. So based on what we've seen here, and we're not saying it works for everything, but based on the evidence we have, we can make our conjecture, our hypothesis. We can say that the sum of the first n positive integers is always just going to be equal to n squared. Okay, isn't that kind of neat? You feel free to try that and see if it works forever. And you'd be like, whoa, who knew? Now you know. You can impress your friends at a party. Alright, biology. Speaking of impressing people at a party, laboratory culture contains 150 bacteria. Okay, when it says culture, that doesn't mean like your family's history and all that. That's shoot, I don't know what it means. Look it up. Culture. It's when you have a little petri dish and it looks kind of like a cylinder, and then you put stuff on the bottom of it, and it grows and it grows and it grows. That's your culture. It's the green stuff. That's probably not the best definition. Ask a science teacher. Okay, so it starts out with 150 bacterias. I'm going to pluralize that. I don't know if I'm supposed to. After 20 minutes, it goes up to 300. So 20 minutes goes by. We're at 300. This is at time 0. You make a chart. Okay. After 1 hour, it contains 1200. So we're going to skip a line here and call this 1200. So we're trying to find a pattern here. We go from 0, 20 to 60. Well, what's in between 20 and 60 is, hopefully you can see that's 40. And if we look at this and we use some common sense, we can say, well, 150 to 300, this looks like times 2, right? And 300 to 1200, that's times 4. So maybe from 20 to 40 minutes, maybe it doubles again. So 300 times 2 is 600. And then 600 times 2 is 1200. And oh my gosh, it works. So make a conjecture about the rate at which the bacteria increases. So we can say it doubles, or it multiplies by 2. It doubles is easier to write. Every what? Every 20 minutes. Which means pretty soon you're going to have a whole lot of bacterias, and you're going to need a bigger dish. Or less bacteria. Put it in the refrigerator until it to chill out. Okay. Last examples. Last bad jokes. Show the conjecture is false. So show that what this is saying, it's making a hypothesis, and we're going to say, no, you're stupid, and let me explain to you why you're stupid. Okay? That's our counterexample. It's our mathematical proof that the book is stupid. Get excited. Alright, so Kennedy is the youngest U.S. president to be inaugurated. So we're going to have to go to Wikipedia and look up the inauguration age of presidents. Oh, no, wait, there's a chart right here. Okay, let's look at the chart. So Kennedy was 43. We need an example showing that he wasn't the youngest guy. Well, good thing we got old Teddy Boy Roosevelt, who is 42. So what is our counterexample? 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 Teddy Bear. Okay. Next one. 3 points on a plane always form a triangle. We haven't really talked about this. What we need to learn in geometry is that when we say plane, we're not talking about this. This is not the plane we care about. Okay. What a plane is, and maybe I can get an actual example in picture form. Heck no, all I get are more planes. Okay, whatever. What a plane is a 3-dimensional surface. Okay, so go away, plane. Go fly off. Just flew backwards. So a plane is a flat. Wait, did I say 3-dimensional surface? Dude, I didn't mean to say that. Plane is a 2-dimensional 2D surface. So it's something flat. So it's kind of like I can draw hold on, I got it here. Okay, so like here is, you could say this is our plane, right? Nice and flat, only it's kind of like a line. You know how we say a line and it goes not like that. That's a bad line. It goes, oh, they're all tiny, I can't see. And it goes like this, and it continues on forever and ever, right? A plane is just like that, only it's in 2 dimensions. So imagine this rectangle, but it goes on forever. So it just gets bigger and bigger and bigger. Okay, you get the idea. So 3 points in our bigger and bigger rectangle will always form a triangle. So all we need to do is to prove just one time that this is not going to make a triangle. So if I say point, point, point. Oh shucks, that makes a triangle. That was bad. So is that drawing? Okay, so how's that going to work? So how, oh how, can I make my 3 points that will not make a triangle? So take a second, think about it, pause it, and unpause it. What if I put my point right here? Now I've made a straight line. Right? Or a line segment, assuming those don't go on forever. Okay, so this doesn't form a triangle because they're all in one line. Triangles don't work that way. So there's our counterexample. So you can put 3 points on a plane and it won't always make a triangle. Take that, math. Okay, go away. You too. And our last one, for any real number x, if x squared is greater than 1, then x has to be greater or equal to 1. And so this one at first you think, well, that's kind of hard to prove, because if you square a number, it's always going to get bigger, right? Like 2 squared is 4. Well, 2 is greater than 1. And if we say, if it's x squared, how do I make a number squared that's greater than 1 where x isn't 1? Well, think really hard. What about the entire other side of the number line? What if we say -2 squared? What does that equal to? Well, that still equals 4. So x squared is still greater than or equal to 1 if x is -2, but x is definitely not greater than 1 because it's negative. So our counterexample here, we could put -2, we could put any negative, and we can say integers to sound fancy. Alright, so as long as x is -1 or less, this first part will still be true. Okay, so while it's true the other way around, and we're going to get into how the order matters. So if we were to say, if our conjecture was x is greater than or equal to 1, then x squared will be greater than or equal to 1. That would be true all the time. But this other way to say if x squared, and I'm probably getting ahead of myself and messing you guys with these if-then statements, but we're going to get way into that, and you're going to learn to hate geometry. You're going to be like, oh, this is stupid. Can't we just do math problems? And I'm going to be like, no, deal with it. Okay, but until then, be happy, and like, comment, and subscribe. Okay, good night.